In the quirky corners of theoretical physics lies a provocative idea. What if every single electron in the universe is actually just one electron? This electron would be tracing a single, convoluted path through spacetime, forwards and backwards in time. This is the one-electron universe hypothesis, first imagined by John Archibald Wheeler in a 1940 phone call to his colleague Richard Feynman. Though largely a speculative thought experiment, it raises profound questions about identity, time, and the structure of reality. The core idea goes like this. Instead of there being many electrons, there is only a single electron whose world line is extremely complex. Each time we observe an electron, we are really seeing that one world line intersecting our slice of time at many points. The hypothesis draws on two key observations. First, all electrons have identical mass and charge, perhaps because they are actually the same entity seen many times. Second, in Feynman's formulation of quantum electrodynamics, a positron can be interpreted as an electron moving backwards in time. Therefore, if the electron sometimes goes forward in time and sometimes loops back, everything we call electrons and positrons are just segments of one tangled world line. Picture spacetime as a four-dimensional fabric. A particle's world line is the record of its existence through time and space. In this hypothesis, that line isn't simple. It loops, twists, and doubles back. At specific points, it goes forward in time, appearing as an ordinary electron. At other points, it goes backward, interpreted as a positron. Because an observer at a fixed moment cuts the world line at many places, the same electron appears numerous times in our present. The hypothesis offers simplicity, reducing the number of fundamental particles to just one electron. It also explains the uniformity of all electrons and plays with the idea that particles and antiparticles are connected by time direction. Wheeler reportedly said to Feynman, "I know why all electrons have the same charge and the same mass, because they are all the same electron." Despite its elegance, the one-electron universe remains highly speculative due to major challenges. We observe far more electrons than positrons, a significant matter-antimatter asymmetry. Particle creation and decay, like electrons created in beta decay, complicate the idea of one continuous world line. Quantum field theory treats electrons as excitations in a field with many independent particles, not a single world line. The backward time travel of segments opens questions about causality and entropy. It remains a thought experiment with no direct experimental confirmation. Even if not physically correct, it prompts deeper reflections about space-time, particles, and time itself. It highlights how time reversal is more than just a mathematical trick, showing up in Feynman's diagrams and quantum field theory. It suggests that the world line concept might hold more significance than we think. Modern reinterpretations explore it as a monistic model where the world line is a braided geometrical object. The one-electron universe may not be a physically accurate description of reality, but it remains a compelling and conceptually rich hypothesis. It forces us to reconsider how particles exist in space-time, how time's direction influences matter, and how quantum mechanics might mesh with the geometry of the universe. In a universe where time is as malleable as space, what we interpret as many distinct electrons might just be many appearances of one cosmic traveler.